on Phobos.
Oh yeah, I missed that, yeah. Yes, I'm going to talk about illumination conditions on Phobos. So I actually thought I was submitting a science abstract, but I'm still very pleased to be speaking in the exploration session. So this is work that's been motivated by the Dream 2 Stickney study that Bill Farrell spoke about yesterday. But rather than just constraining ourselves to Phobos, we thought we might as well just look at to Stickney, we might as well look at the whole of Phobos. So here's the motivations. So from a science perspective, illumination conditions inform thermal conditions. Then from that you can kind of infer things about volatile sequestration, whether or not you can retain volatiles in the subsurface. Whether or not you've got cold traps where things can be delivered to. That kind of obviously ties into volatile transport, so exospheric processes. But also, you can kind of use these predictions as proxies for solar wind implantation, so for space weathering, because pretty much, protons and photons follow, quite similar paths, and so if photons are getting there, then probably the protons are too. And of course, surface charging through the photoemission of electrons. So the big sort of improvement in this study over previous ones is shape. So the shape is really important. So previous studies of the thermal environment and volatiles and that kind of stuff treated Phobos as either a sphere or a triaxial ellipsoid, and really it's not. It's a very sort of irregular shape, and that makes a huge difference for illumination. And of course, these things all feed into exploration too. Obviously, it helps to be able to see stuff, so it's good to know where the lighting is. You can sort of optimize your solar power resource. You can also identify cold traps, and that maybe have resources for ISRU. And of course, thermal constraints on operations. Sometimes you don't want to be too hot or too cold. Okay, so this work kind of follows on from a study we did just prior to the Dawn mission arriving at Vesta, where we took our illumination models and we looked at the average conditions over one sort of Vesta year, and use those to estimate average temperatures. And this is a map of Vesta, so based on a Hubble DEM sort of shape model. And okay, so this is color coded by average temperature. And there was a study by Shogofer that said that if your average temperature stays below 145 Kelvin over a year, then that means that you can have stable water ice in the near subsurface within the top few meters. And so when we kind of looked at this, so there's 145 Kelvin, and there's a sort of the contour there. Then you can see that pretty much the polar regions, sort of about half of Vesta, could have subsurface ice based on that criteria. And obviously we're not saying that ice is there, but it could be stable. The conditions are there for it to be stable. And so this kind of ties in quite nicely with the geomorphological evidence for transient water flow on Vesta that was discussed by Scully. So there's kind of quite a nice time with that. So this is quite an interesting, important thing to look at. Okay, so for Phobos, we use the Thomas shape model. That's a 2 by 2 degree resolution, and the reason why we picked this is because it's detailed enough to sort of pick out features like here's Stickney, you can see quite well, and there's even Limtok, and there's a Drunlow crater there, so you can pick out some of the major features. But it's not so detailed that it's going to take an awfully long time to kind of run the simulations. And so, Phobos, as people have mentioned before, is entirely locked around the Martian equator, and there's sort of Mars is in that direction. This is kind of like the round direction for the object orbiting around Mars. And so the semi-major axis is at about 2.8 Martian radii, and the orbital rotation period is sort of 7 hours and 39 minutes. So, just a quick comment on Mars orbit. So, like I mentioned before, we're kind of focusing on present-day conditions. And this is sort of Mars-Sun distance here as a function of time. And so we kind of run between the last two perihelia, and this is the sort of semi-major axis running across here. So one thing to note is that the Mars orbit is a lot more elliptical than the Earth orbit, and so that aphelia and perihelia are about separated by 21%. So there's a 21% difference between the two. And so seasons are different lengths on Mars and Phobos, and so you kind of got this very kind of sort of weird process going on there. It makes it a little bit more complicated. So here, looking at Phobos orbits and seasons around Mars. So there's Mars in the middle, and sort of the Sun is in the sort of positive X direction. And I've shown the orbits of Phobos every 1/24 of a Martian year, and you see kind of build up this pattern here. Okay, right. And so I've color coded each point by whether or not Phobos can see the sun or whether it's in Mars eclipse. And you can see here that there's a fairly substantial region where it kind of passes into eclipse behind Mars, and so that accounts for about 5.6% of Phobos's time time spent in eclipse. And as I probably should have mentioned before, Phobos's spin axis is kind of normal to its orbital plane, and so that kind of means that it kind of has the same. That's why it has the same seasons as Mars, and so relative to the Sun, it has an obliquity of about sort of 25 degrees. Okay, so some quick comments on the simulation setup. So I mentioned about focusing on present-day conditions. Now, in previous studies, people have assumed that obliquity and other parameters varied with Mars in the past. So Mars's obliquity is known to sort of vary, and people typically assume that Phobos would pretty much just track that. So with the simulation itself, we include the effects of topography, so that basically local horizon elevation, and so we calculate that effect at each point on Phobos and using the shape model. And that gives us three main outputs, which is solar visibility, which is how much of the sun you're seeing, so whether you're seeing the full sun, no sun, or some fraction of the sun. And that fraction of the sun can be very important for regions near the poles where, if you weren't doing that, properly, that you could assume you're seeing the sun when you're not, and vice versa. And then solar incidence angle, whoops, that's the next one, and then solar flux comes from that. And so the time step we're using is 10 minutes, and so that's about half an hour local time. And we found that we were getting pretty decent convergence. So for this 10-minute case, the differences between that and the 1 hour time step were kind of less than 0.1%. So that's pretty good. So in the runs I'm showing you, we've ignored the Mars eclipses for now, and so that means that we're going to get a small overestimate on the Mars-facing hemisphere. And yeah, so the plan is to incorporate that next. But okay, so here's the shape model kind of mapped out. This is also latitude versus east longitude, and there's the sub-Mars points. That's the point that's always facing Mars. And in the middle here we've got the far side of Phobos between 90 and 270 degrees, and so that side is always facing away. And so here you can kind of pick out, this map's good enough that you can pick out some of the features I showed earlier on, so you can see there's Stickney and Limtock and Drumlow and a few other features. Right, so first up, these are our predictions for average solar visibility. And so typically for a sphere, you'd expect that to be sort of 50%, sort of half. You see the sun about half the time. But because we've got a more complicated object, and there's an axial tilt and a few other things, it's a little bit more complicated. So we find that in the southern hemisphere, we're getting kind of regions where you're, some craters where that you're only seeing the sun for say 10-20% of the time. So pretty well shadowed. Then you also, near the poles, you're seeing areas where you're seeing the sun for over 50% of the time, and that's due to the irregular shape. So in the same way, say on the moon, you kind of have points of eternal light. You kind of have the same thing with Phobos, but because Phobos is such an odd shape, the effect is exaggerated. You kind of got around these crater rims here, especially in the north. You're seeing the sun, an awful lot of the time. And so it's kind of good to know this because from an exploration point of view, trying to be relevant to the session, that would be a great place to put your solar panels. So you always get a lot of sun. Okay, and this is just incidence angles, another output. So just quickly comment here, you're seeing features that you expect. So say up here now near Drumlow crater, there we go. You're seeing sort of poleward, equatorward effects due to incidence angles here. So that's kind of the sort of thing you'd expect to see. Right, so next up, so then from those we can then calculate the average solar flux, and so what we do is we kind of then normalize this to the semi-major axis distance, which is about just over 1.5 AU, and sort of try and correct for that sort of variation in Mars's orbit, and so here I just might comment quickly that you kind of see things like you can see sort of effects of crater and crater double shadowing. So here's Limtock inside Stickney, and you kind of see it's kind of being doubly shadowed, and that sort of gets picked out by this. So then you can take this and then multiply it by the Mars solar constants at the semi-major axis, which is 586 milliwatts per meter squared, and then that kind of tells you what's the average sort of solar power you're getting to each point on Phobos. And You see in the very cold regions, you're getting, much less than 40 milliwatts per meter squared, so not a lot of power. Okay, so then next up we can take that and we can have a quick stab at making estimates of the average dayside temperatures. And so for this we need to assume a Bond albedo. And so for Phobos, you pretty much assume it's about 0.05. And so just to give you some sort of context, that's about the same as fresh asphalt. So that's kind of, it's a real light sponge. It soaks up, almost everything. And so that means you're going to get very hot. And so with this calculation, basically it's the dayside component of the standard thermal model is what we're doing here. And you can see that we're getting, so the very hot regions, you're getting above 300 Kelvin. So that's kind of, above room temperature. That's pretty warm. So especially there, Stickney, gets quite warm during the day. But then other regions near the poles, you're getting, dropping down to sort of 220 Kelvin, so sort of minus 50-ish degrees Celsius, so it's pretty cold. And you can see also that there seem to be sort of steep temperature gradients between different regions because of the irregular shape of Phobos. And so that might be operationally important to bear in mind. Okay, so then we take a very rough estimate of what the average temperatures will be over the whole of Phobos over the whole year. So doing the same sort of thing we did for Vesta, and kind of looking to see, where you're getting below 145 Kelvin, so on this color scale, kind of there. So sort of looking at the sort of greenies, sort of cyan colors, and sort of bluer. And to do this, we just assume a nightside temperature of 80 Kelvin, so you can kind of argue whether or not it's a good estimate, but just to give, to get started with that. So we think this probably overestimates the temperature in the polar regions and underestimates them in the equatorial regions. So this map, the main point here is that we're seeing a lot of regions with averages less than 145 Kelvin. So it's plausible, perhaps, that there are regions on Phobos where you could stably trap water ice in the near subsurface. So I'm not saying there is ice there, but if there were, it would be thermally stable. Okay, so then in summary, so the main point was that Phobos topography has a significant influence on illumination and temperature, so it's very important to take into account. So under present-day conditions, it's plausible that you could have water ice stable in the near subsurface in some places, especially in polar craters, especially in the southern hemisphere. There seem to be a lot of locations. So there could still be active cold trapping sites and or places where you could store older volatile deposits, but that sort of depends on past obliquity and whether or not these regions have stayed are highly shadowed for a long period of time. So these could be possible resources for exploration, something to look into. So one of the nice things for exploration is that some of the potential cold traps are near regions with high solar visibility. So it means you can kind of stay there, have power, but also there are fairly modest daytime temperatures near these regions, so you can kind of operate outside the cold trap, fairly easily. So these kind of places could lend themselves to being explored. And just a little comment about Dream 2 with the Stickney crater. So that's likely very hot during the daytime. That's one comment on that. But there's more work to do, and so this is definitely a work in progress. Thanks.
We have time for a few questions.
Hi, Tony Dobrovolskis, SETI Institute. A comment and a question. If I recall correctly, I think that Deimos has a big saddle at the South Pole that might be interesting to look at. And I'm sorry, I didn't quite catch whether the modeling included reflection and re-radiation in concavities.
No, so this is just direct illumination. Yeah. So we kind of figured that if these cold traps weren't plausible when we're just considering direct illumination, then it's not worth going to all the effort of factoring in scattered light.
All right. Any other questions? Okay, thank you, Tim.
Right, thanks.